It's Astrophysics. This is Cosmology lesson 2, and this one's on binary stars. So, Doppler shifting spectra. So there's some spectral lines for a stationary source. If it red shifts, you'll see it shift obviously towards the red end of the spectrum to the right. Blue shift shifts to the left. So you may see these in examinations. And it'll ask you to calculate, you might need to get the difference in wavelength. So obviously that scale at the top would be more prescriptive if that was so. But you get difference in wavelength and then perhaps calculate recessional velocities. So let's start with a recap question. So if you want to have a go at this one. Right, so the hydrogen alpha spectral line of a distant galaxy occurs at a wavelength of 680 nanometers. In the sun, this wavelength is 656 nanometers. Calculate the recessional radial velocity of the galaxy. So what we need to do, we need to get the change in wavelength divided by the wavelength is equal to the source wavelength, which is what it should be if it wasn't moving away or towards us, equals V over C. So the change in wavelength is 680 minus 656, which is 24 nanometers. And divide that by the source wavelength, 656 nanometers. And then multiply through by speed of light. And that'll give us the recessional radial velocity, which is a rather fast 1.1 times 10 to the power of 7 meters per second, or around 11,000 kilometers per second. All right, if you got that, well done. Let's move on. So what we're going to do is look at the Doppler effect with binary stars. So a binary star system consists of two stars in mutual orbit. They orbit around the center of mass between the two stars. They orbit around each other. So the two stars are often too close together to be resolved by a telescope as separate stars. However, as they orbit each other, they'll be moving away and towards the Earth. So what you'll get is you'll be looking at a star and you'll get blue shift and red shift simultaneously. So they'll be producing red and blue shifts which can be measured. And this type of system is called spectroscopic binary. And from the Doppler shifts, from the measurements that we can take, the orbital speeds of the stars can be found, and also their radius of orbit. So we've got a binary star system here. So we've got star A and star B. Got a line of sight, so that'll be us on Earth. So to start with, as star B is coming towards us, that'll exhibit blue shift. Star A is moving away from us, so that'll be red shift. So the initial spectra might look like this. For reference, for the dashed lines, the H alpha line from a stationary source, so that'll be from the sun. So red shifting star A, blue shifting star B. As they rotate, obviously as they're not coming straight towards us, we're only looking at a component of their velocity moving away or towards us, so the amount of red shift and blue shift will diminish. When they're in this position, not moving away or towards us, there'll be no red shift or blue shift, and then they'll switch. So star B is now starting to move away, star A moving towards us, and that'll keep happening on repeat. So in this example, star A is much more massive than star B. And this results in the orbital radius and speed of star A obviously being less than star B. Right, so I've got a question for you to do. It's a little bit tricky, but we'll see how you get on. All right, let's look at this one then. So this is a spectral line of certain spectroscopic binary. It merges once every 4 years and splits to a maximum displacement of 0.036 nanometers and 0.015 nanometers from its laboratory wavelength, which is the source wavelength of 656. So the first thing we need to do is calculate the orbital speed of each star. So we're going to use Doppler shift equations. So we'll do the slower star first. So that's going to be the least amount of shifting. So 0.015 nanometers divided by source wavelength 656 nanometers. We're using the change in wavelength over source wavelength equals V over C. So we're going to rearrange that to find V. So we've got to times through by C. So times 3 times 10 to the 8. So that gives 6,860 meters per second, or 6.86 kilometers. Then we'll do the other star, so that's 0.036 for the change in wavelength, nanometers, divided by 656 nanometers for the source wavelength. Times through by speed of light. That gives us 16,463 meters per second, or 16.4 kilometers per second. So then we need to get part 2, or B, which is the radius of the larger orbit. Now the larger orbit is, the time period of these stars is exactly the same. So it makes sense intuitively that the one that's moving fastest must be further out to have the same time period. So what we're going to use for this one is V equals 2 pi r over t. We know the velocity. Now the time period, so it says that the spectroscopic binary merges once every 4 years, which occurs every half rotation. So the time period that we're looking at is 8 years. So what we need to do is to convert that into seconds. So we're going to do 8 years times 365 days in a year. You could do a quarter, it won't really change your answer that much. Obviously it's taken into account a leap year. Times seconds in a day, which is 60 times 24, which is 86,400. So that's 2.5229 times 10 to the power of 8 seconds. Then we do V equals 2 pi over t. In fact, I've got it there, so I'll just rearrange it for r. So Vt divided by 2 pi gives us the orbital radius. So the velocity of the larger orbit, 16,463, times the time period, 2.5229, times 10 to the power of 8, divided by 2 pi, will give us the radius. And you should have got 6.6 times 10 to the power of 11 meters. If you compare that to the sun's orbit, well, the Earth's orbit around the sun, that's 1.5 times 10 to the 11, so it's significantly larger. Right, hopefully that's given you a good understanding of binary star systems, and this type of question is really typical on examinations, so hopefully that one went well. Thanks for watching.